Hi everyone, I'm Piotr Moczurad. You may also know me as Pete Urinsky from Discord and Twitter and such. And yeah, it's my pleasure to present a short tutorial on smart contracts in Ink, specifically on the Aleph0 chain. But actually, I think you'll find a lot of the principles will apply to, well, smart contracts generally, some of them, and all of Ink smart contracts definitely. So let's dive right in. Yeah, so I felt compelled to put a definition of a smart contract here. It's not really important, but I think it's worth noting that basically a smart contract is a program that executes on the blockchain. Actually, this analogy works quite well along the way as we go. So the smart contracts give way to some interesting use cases. I think the most prominent one being DeFi, so decentralized finance, but also digital identity with the whole KYC, KYB use cases. And yeah, you may do, supply chain and provenance tracking in some big company. Also, a pretty exciting use case is certificates of ownership, be that art, real estate, licensing, or tickets. But of course, you're actually encouraged to come up with your own use case and implement it. So let's hope, after this presentation, you'll be interested enough to dig deeper and to deploy your own smart contract and an application on the blockchain. So maybe a slide forward. This presentation is supposed to be quite general. So I wouldn't expect to learn all the ins and outs of blockchain development or Ink even, but rather after this, I would like you to have a basic overview of how to approach blockchain development, well, smart contracts specifically, and yeah, I will encourage you to explore on your own and yeah, just start developing. So for now, we're gonna start with some, well, let's say theoretical introduction, because we're gonna look at decentralized finance, another definition that's, well, from Wikipedia. So yeah, that's a very credible source. So basically, decentralized finance, you can think of it, well, you want to interact with some financial instruments without relying on some trusted intermediary, exchange, bank, or whatever. You want it to be censorship free and everything. So you do that on the blockchain in form of smart contracts. And here as well, we have some very interesting examples, including decentralized exchanges like Uniswap or Common that will be coming to Aleph0 quite soon. You have lending protocols, trading, crowdfunding platforms like Angel Block, for example. You have payment protocols and many more actually. That's I'm leaving this up to you to explore. And we're gonna look at one example because I find it quite interesting and actually quite educational and also quite beautiful in its simplicity. So how there are, well, centralized exchanges that keep the order books, and you can think of it as a building, and there's some computer running in the building, but actually there could just be a physical book where you keep the limit orders and everything. And well, the problem here is that it's completely permissioned, and someone could just restrict your access or say, okay, now I'm taking custody of your funds. So I would like to compare that with the new way, specifically a decentralized exchange. And it's cool because the decentralized exchange is running as a smart contract on the blockchain. So there's no single authority, right? The contract is just a program that's executing, and it's actually completely transparent because you can inspect its code and see what it does. So you will never be surprised. And we're gonna look at the automated market maker concept here, but let's just note that this is not the only way to do a decentralized exchange. You can also actually do an order book. something that's very interesting. But the AMM approach is, well, it's kind of beautiful in its simplicity. So for the sake of this presentation and to keep it, light and interesting, I'm going to just, mention a few words about how this works. So basically, the exchange keeps a liquidity pool, or actually like maybe liquidity pools. So if I want to provide the liquidity to the exchange, I just take some, well, let's say I take some of the tokens, actually a token pair, and I deposit 100 of token 1 and let's say 200 of token 2. So now the exchange has a pair, and you can kind of see that the ratio is 2 to 1 for now. But in general, what the exchange will try to do is to, and this is slightly simplified, but I think it actually illustrates this quite well. So the exchange will, for a single pair of tokens, the exchange will try to keep their product as some constant value. Well, let's call it K. So now you can see that if I do a trade and actually want to trade sum of token 1 for token 2, it's very easy to calculate what's the amount of token 2 that the exchange has to give back to me, right? We actually have it here illustrated a little bit better. So what we will do, let's say I want to exchange 10 of token 1 into a certain amount of token 2. So I just give the 10 to the exchange. It adds it to the amount of token 1, then it increases. So in order to keep the K constant, the amount of token 2 must decrease, and this amount, and of course you can calculate it quite easily. And the decrease in token 2 is basically what I get back as the exchanged token. Now notice that the K here is constant for a certain liquidity pool. When I provide the liquidity to the exchange, the K basically will need to get recalculated. So yeah, so I just wanted to show you how, a very simple idea, and actually the resulting smart contract is also really simple, and it's very expressive, and it can work as a fully functional product. This is kind of like Uniswap v2 concept, and also actually a neat property of this is that the exchange never runs out of liquidity, because if you even take a look at this curve here, you will see that it just approaches zero on both sides, but never quite gets there. So this is a cool property, right? But we are seeing how expressive you can get with smart contracts, and how actually powerful the whole concept is. But well, it's actually handling vital assets, and user deposit their funds and everything. So of course, well, we need to make sure that the contracts are written properly, and there's no possibility of any exploits or attacks or malicious behavior. And yeah, here it's stated kind of like a joke, but the grand theory of hacks, if you may. But my stance on this is that basically the exploits happen in the places of your code when you're not 100% sure what the code does, right? And it sounds very trivial, but this is actually the case, right? If you have a language that's not safe enough by design, or it's especially easy to shoot yourself in the foot, the exploits, of course, will happen much more often. And yeah, this is kind of this kind of will lead me on to talk about Ink, which I think is designed really well, and doesn't offer you as many ways of shooting yourself in the foot, and it's quite safe. But in general, and this applies to, I guess, all code, but smart contracts and smart contracts in Ink specifically, you'll need to watch out for input validation. Basically, if the input is not validated and your contract can get something it does not expect, well, there you have it, a attack vector. Actually, and this is, well, basically my background as a functional programmer talking, but any operations that mutate the state of the contract are inherently dangerous, right? So Of course, you cannot avoid them, and they are essential to the functioning of your program. But it's actually nice to kind of make them kind of, well, separate, or treat them with special care in your contract. Stuff like the code repeating itself. So not only loops, but especially recursion of any sort, and contracts calling themselves, a really important area to focus on, and a lot of attacks happen there actually. Especially when you add like catch-all methods like Solidity's fallback, and any implicit operations. This is something to really watch out for. So yeah, so to kind of demonstrate this idea, I wanted to talk about the famous DAO hack, which happened, of course, a long time ago, and the problems have since been fixed. But it actually illustrates quite well what I wanted to convey here. So the way this happened is that there was a DAO contract, which, for to focus our attention, it basically allowed you to deposit and withdraw some ETH, right? So, and now it's important to note that the way Solidity works, you can have a fallback method in your contract, which basically says, okay, if the contract is asked to do anything that it wasn't programmed to do, the fallback is like a catch-all method that will handle this, right? Additionally, and it's the same in Solidity and in Ink, but handled a little bit differently, you can send like the chain's native currency to the contract. So in this case, ETH. And in Solidity, in order to handle the transfer of actual ETH, you need to have the receive method. But if there's no receive method, the contract falls back onto the fallback method. So now for this, we would need to take a look at the code of the DAO contract. But the gist of it is that the contract was, when asked to withdraw some ETH, the contract was basically transferring the ETH to the caller, and only then decreasing the balance of the caller in this contract. So what someone did, and the classic names used in cryptography would be Alice, Bob, but here it's well, I thought it would be funny to call the attacker Malice, just because it sounds like something very evil. So what Malice does is, well, she first deposits 100 ETH, of course, can be any amount actually, and then asks the DAO contract to withdraw the 100 ETH. And of course, the contract checks if she actually has this balance. Yes, sure. And then the contract issues a transfer to Malice. Now, Malice doesn't have the receive function in her contract, so it falls back to the withdraw, it falls back to the, well, fallback method, where they actually put another withdraw. And remember that now it gets executed in the context of like a single execution step. So the DAO contract hasn't yet progressed to the step where it decreases the balance, right? So basically what happens is the contract enters the withdraw method again, the DAO contract, and the balance hasn't yet been decreased. So it says, okay, I have the funds to transfer to Malice. And basically this loop happens as long as the DAO contract has any funds. So this is how you were able to drain the whole contract. And actually, you can see that the fix is very simple. You can just flip the order of the lines and first decrease the balance and then actually make the transfer. But, well, we live and we learn, right? So this is just, an educational example to serve as a warning to, well, first of all, avoid any implicit and catch-all methods like this. And secondly, this underlines the importance of actually writing your code in a very diligent and cautious fashion. Yeah, so let's move on. So let's talk about where we are gonna deploy our smart contracts and what platform are we gonna use. And well, for the sake of this discussion, we're gonna use Aleph Zero, which is a layer 1 proof of stake blockchain with some very neat privacy features that we are building out right now. Sub-second finality times and also block times, actually. Extremely low transaction cost. I cannot really read this number very well, but you can see that it's like a small fraction of a zero, which actually is quite crucial to smart contract development, right? It influences how you approach the development, and maybe you won't have to spend like hours tweaking the bytecode, because you can just write out your logic and it will be priced reasonably. And of course, it gets smart contract in Ink, introduced not that long ago, but they're on the mainnet now, and a lot of people are building out their use cases. It's a quite exciting time to be on the chain. So let's take a look at how can we implement the smart contract in Ink. But first, here's some useful links for you. You can scan the QR code. I think the slides will be attached, so you'll be able to click on the links. The first one is the main Aleph Zero website, and actually you'll be able to get to all the other links via this website in like 1 or 2 hops. But then you have the Aleph Zero documentation, the Aleph Zero developer portal, which contains links and like resources to all the Ink tutorials that you will need. And then the developer wallet, test.a0.dev. Of course, we support other wallets, but this is like the, well, let's say feature complete one for developers specifically, and for validators. And then last but not least, the contracts UI, which allows you to upload and interact with your contracts, obviously in quite a user-friendly fashion. We're going to actually touch upon that later on in this presentation. So yeah, so first of all, what is Ink, right? The language that we use to write the smart contracts. It's an EDSL for Rust, so an embedded domain-specific language built on top of Rust. So it's not a separate language. You don't have to learn something entirely new and the whole ecosystem. Basically, without loss of generality, we can say that this is a subset of Rust with some additional macros. So not all EDSLs are created equal, and Ink is on the more minimalist side, let's say. So it doesn't add any fancy constructs. It's just a subset of Rust and some macros that you'll need to include. But on account of being essentially a subset of Rust, it inherits Rust's benefits. So being modern, really, this is a well-researched language with a lot of modern features. You won't get to use all of them when writing smart contracts, but yeah, it's still good to keep that in mind. It's type safe. I would say as type safe as a practical programming language can be. It's memory safe, and actually I encourage you to dig a little deeper on Rust's memory management. We're going to touch upon that very briefly, but it's a very interesting read. And again, when writing smart contracts, you won't have to dive very deep into how Rust manages the memory, lifetimes, borrowing, and everything. But still, I think it's a very interesting concept, and yeah, one of the best implementations I've seen personally. The tooling is quite good. Obviously, it's in terms of smart contracts, Solidity is more mature and has way bigger tooling, but Ink, and Rust is catching up really quickly, and I think there's a lot to like. And of course, Rust is universally liked in the Stack Overflow survey. Rust is coming out on top as the most liked by developers programming language. I think it has been for a few years now. So now the let's say flavor of Rust, or the backend that we're going to use for Rust specifically for smart contracts development on WASM chains is obviously WASM, and so WebAssembly. And I don't think I need to dive deep into the benefits here, but it's ubiquitous. So the browsers supported, some different execution environments supported, the chains supported, of course. It's fast and secure. And yeah, since we were talking about WASM, I have a it's like a personal, interesting. Oh yeah, here, like something I was quite surprised by, but in a good way. So when you think like, what is WASM, right? Because you know that it's some assembly or binary format that executes, wherever you want it to. So yeah, it is indeed an efficient binary format that executes on a stack machine, which we're going to get to in a second. But actually, if you take a WASM file and decompile it into like, well, mnemonics, you will see that it has a lot of parentheses and in general looks like a Lisp, which some of you might find familiar. I find it quite funny that one of the oldest programming languages still, finds its way to the mainstream actually. And yeah, this is purely, and fun fact, let's say, but the way that it executes is actually really simple and similar to the languages like Forth or actually even the early JVM. So if you have like an addition, you basically parse it into like, say, well, 7 plus 5, right? You parse it into first like the, well, reverse Polish notation, but then you start putting the elements on the stack, right? So if I have a function, oh, actually, when you look at the function here, you will see that first you have the params, then you have the results. So you first, get the left-hand side, then you get the right-hand side, then you use the add function on both of those. So yeah, it's like that. When you're parsing this expression, you're just basically putting the first operand on the stack, putting the second operand on the stack, then putting the operator on the stack. Now the whole execution is that simple and looks like this. Okay, pop something from the stack. If it's a function like an operator, we'll see, okay, how many arguments does it have? Okay, we can see that addition has 2. So we have to pop 2 arguments from the stack. Of course, here they are like concrete numbers. If they were operators themselves, we would just continue this popping thing until we get a result. But here we just pop 5 and 7 from the stack. We know that now we can apply the plus to them, and we have 12. And basically we execute until the stack contains only one result. Or actually, well, it's empty because we will pop it in the next step anyway. So yeah, this is how one of the most popular, well, assembly formats works, and I think it's quite beautiful in its simplicity. So coming back to the Earth, coming back to Ink, this is a comparison chart between Ink and Solidity. It's actually taken from the use.ink website, which I recommend. I think I'm linking it further down below. But this is a comparison of features of Ink and Solidity. And of course, I don't expect you to kind of like analyze this and memorize it. It would be completely crazy. But what I wanted to convey here is that pretty much every concept is shared between Ink and Solidity with some slight differences, but on like the level of ideas in the code and of the concepts, they are actually quite similar. So you can think of it as a slightly different flavor when writing smart contracts, and not something that's entirely new and you have to throw away all that you've learned. No. You can still apply that. You will use a slightly different type system, well, safer actually, and you will have slightly different storage entries. This is actually quite important to the speed aspect and performance aspect, because, well, the 256 bits as the only storage entry by default in Solidity and, well, in EVM gives you a lot of overhead. And yeah, I'm kind of glad that Ink chose the variable storage entry. So if you need to small store numbers, you can use small variables. So this actually plays a big part in the efficiency of the whole thing. But in general, the concepts will be familiar if you're coming from Solidity. So you just learn a bit of new syntax, maybe a bit of the new type system, but nothing crazy, and you're good to go. So this kind of like debunks the myth of like, oh, Rust has a very steep learning curve. Well, Rust may have that curve, but Ink is a subset of Rust and should be quite familiar to Solidity developers. Yeah, so now a more practical look at developing smart contracts in Ink. And again, this is just to give you an idea. This is not a complete guide by no means. For that, I encourage you to go to the links that I pasted before. So the developer portal and the Zero documentation, and actually the use.ink documentation, which is great. I love it. So, but here, to just give you an overview, what will be required to write your smart contract. Well, of course, you will need to install some dependencies, some tooling. Quite obviously, you know, Rust compiler, and this will also install Cargo, which is like a package manager slash build tool slash general utility tool for Rust, and then you will install Cargo contract, which is basically an extension of Cargo to also handle smart contracts in Ink. Once you have all that out of the way, we can create the contract. So, you know, like it's a scaffolding or bootstrapping similar to what you might be used to from, I don't know, Rails, Django, or whatever you used in the past. Then you obviously write your code. So the Flipper code will be there written for you when you run Cargo contract new, which is quite cool because you will have the general structure of the code and you won't have to remember what macro you need to use. It will just all be there. You can just make your changes. You can, of course, start from scratch and just build it out yourself, whatever you think is the most efficient. And then you will compile and test your code. Well, first, the Cargo test command. I'm using the +nightly here to use the nightly toolchain to basically get like the latest, greatest of Rust packages, which is required by some of the libraries we sometimes use for the smart contracts. In general, I think for like pretty simple smart contracts, you could get away with just using Cargo test and Cargo contract build. We'll actually look at the Cargo contract build a bit later. You'll also need the -- release argument probably, but yeah. So the effect of that will be, yeah, an attempt at the joke here. So 2 artifacts: the WASM blob, basically the binary code, the metadata, and the 2 above bundled together. So you will probably almost always interact just with the contract bundle. I try to, you know, include like an off by 1 error because, yeah, it can be tricky in programming. I now realize that maybe it's not as funny as I initially thought, but well, there you go. Yeah, right. So I will also show you how to deploy the contract to the network and interact with it, but that's postponed until the end of the presentation just to keep the structure a little bit better. Right. So I thought that a good example of for you know, developing a smart contract will be probably the most ubiquitous smart contract that we all interact with on, well, daily basis, and that's going to be the PSP22 token, or ERC20. It's well, ERC20 is the Ethereum version. PSP22 is the Polkadot /Substrate /Aleph0 version. So the differences are minimal. The PSP22 is actually a bit, well, has a bit better error handling. Well, let's see. But for the sake of this presentation, I decided to call it a Pete coin. It's not a real coin. It's just something to to make for, you know, for the demo. So yeah, let's get to it. This is the ERC20 standard, and you can see that it's actually very simple, right? So this basically tells us what an ERC20 contract needs to be able to reply to, right? So if you ask, you need to be able to ask it for its total supply, of course, balance of a certain address. Actually, let's skip allowance and transfer for now because it's yeah, we're gonna keep it short and sweet. Then you need to be able to transfer some tokens, some amount of tokens to a certain address. And yeah, our contracts will return a, well, better result, like not a Boolean value, but a result. We're gonna, you know, touch upon that later. Yeah, there's also approve and transfer from, which is like you can basically say that someone can spend your tokens on your behalf, and how many tokens they can spend, you know, is dependent on how many tokens you actually approve, and then the transfer from is the method for transferring the tokens on someone's behalf, right? The events, of course, the contract emits events, but we haven't explained that yet, so let's leave that for later and just move on. Right. So, of course, like I said, Ink is an EDSL, so it's Rust with some macros that you need to include. You don't actually have to worry about remembering the exact syntax here, because when you type cargo contract new in your shell, all of this will be generated for you. You'll be just in charge of adding the logic and yeah, basically the logic and the tests maybe. So the macros in general start with, well, at least for the sake of this discussion, start with like a hash, or how do you call it? So the first one has to do with, Ink contracts not using the regular standard library. They have their own little standard library just to make it compile to WASM easily and not be bloated or anything. Then there's the Ink contract macro. Oh yeah, so you put the Ink contract macro on the module, and a module is basically a container for some items. Like, you can think of it as a namespace if you're familiar with C++, maybe with some a little more expressive than a namespace, actually, I would say. And use is, well, I want to say an import, but it actually is not an import. It's just introducing some, binding a name, well, like a longer path to a name, basically. So this is actually quite similar to what you get in C++. So, for example, the Ink contracts don't execute any code when you do a use, right? So this is different than, say, Python, for example. So in that sense, it's a use and not an import, right? Right. So we're gonna like dissect this in a second, but what the Ink contract macro does is initialize some stuff, initialize some aliases so that the development is a little bit easier, but also it enforces certain invariants, like the contract has to have at least one constructor, it has to have exactly one storage struct, and I think it has to have at least one public message that it can reply to, and so on and so forth. We're gonna see concrete examples in a minute. So yeah, I mentioned storage struct. It's there down below, and yeah, this is what it looks like. So we're gonna use a mapping to keep our balances. So we need to, well, we could just type out the fully qualified name here in the balances, but that's just not really convenient when you're using it a lot. So we're just gonna shorten it and say use Ink storage mapping. Then you'll be just able to say mapping, because it will bring this into our current namespace. Now, the important thing is the Ink storage macro, which basically what it does is tell the compiler or the chain's runtime actually to put this particular struct in the contract storage. So this stuff will actually end up on the blockchain, right? And it's quite important to be, maybe not super cautious, but you need to think about what you're putting in the storage, because basically, just by virtue of it being on the blockchain, like I said, Auth0 is cheap, but still, if you store a lot of stuff like images, videos, and whatnot, you'll end up with a very expensive smart contract. So you need to be smart about this. Basically, there are ways of, like put the heavy stuff off chain and just keep some commitments on chain. You can read about it in the web. So yeah, I actually have 2 slides about this, so I'm gonna need to switch them in a better way. So I'm gonna be talking about Rust here a bit, just to give you some context. If you already know Rust, you'll probably be bored, but hey, this aims to target a wide audience, so let's let's talk a bit about Rust. So struct is basically just like a class, but the important thing is that there's no inheritance. So some of you might associate inheritance with subtyping, but actually this is not the case. Inheritance is just one way of doing subtyping, and Rust has its very own subtyping, maybe not as easy to use as in Java, but it works. It's actually very interesting. But for the sake of this discussion, the structs don't have any inheritance, which I think is a very good decision. It makes the code so much clearer and actually structured a lot better. Inside the structs, we of course have fields. Fields have their types declared here. By the way, balance is one of the types that is given to us by using the in contract macro. Now we will be able to access the fields just like you would access a field of any object in an object-oriented programming language. So struct.field. So here we would have struct.total supply or balances. Now, the interesting part here is the mapping itself, actually. One of the most common data structures in smart contract development, I would say. And here we are kind of like making like a very small bank. Not really, but well, this is maybe a good analogy. So we need to keep the balances of the accounts that are using our contract, right? So the mapping is basically from an account ID. So this is just a regular account on the blockchain of choice, in our case Alex0, and from the account to the balance. And an important thing to note perhaps is that this account here is actually not some weird abstraction. It's basically the account number you use for interacting with the blockchain. So yeah, when interacting with this smart contract, you don't need any additional accounts, or you don't need to do any specific actions. You just can interact with the smart contract, provided you of course have some balance for the transaction fees. Right. Like I said, the balance is a built-in primitive given to us by the in contract macro. Then account ID is actually the same. Those are just type aliases for some. Balance is actually an unsigned 128-bit integer. If you're migrating from Solidity, by the way, as an aside, and you need the 256-bit integers, unsigned integers, you will need to use the library from the crates.io website. You can Google it very easily. Right. So moving on, there's also the interesting derive default macro. So this basically instructs the compiler. We won't get very heavily into the interfaces, but let's say that what this does is allows you to write, give me the default struct like this, and it will most probably, the default implementation is basically quite natural for most of the structs. Like, whenever there's a numeric type, the default is probably 0. Whenever there's a container of some sort, or like a list or a mapping or an array, the default should probably be an empty container, so empty array, empty mapping. Actually, if you're more into algebra, the default here is actually like the 0 of a monolith, if that intuition helps you in any way. And yeah, once the struct has the default method implemented, we will show you how to do it manually later in a slightly different context. Once it has the default method, the default interface implemented, you can use the default method, and it will give you the like a 0 instance of this one that you can safely use to initialize stuff, for example, right? So for example, when we're initializing the contract, initially we'll create a default struct that basically has everything empty. Yeah, so the macro on the previous slide, what it does is basically tries to derive an implementation like that, right? So this is a Rust implementation of a trait for a particular struct. And basically, this tells the compiler that you will be able to call the methods from this trait for the instances of this struct. So it only has one method that's default, and it just gives you back self. So self in this context is basically default. And what it does is it just creates an instance of the struct, and it actually delegates the default implementation to the implementations for each and every one of the fields, right? Fortunately, both total supply and so like the balance here and the mapping have default implementation, so we're good to go. The compiler can derive it by itself. You don't need to actually worry about it too much. Yeah, so the next thing that's important in the contract is its constructor, which we will put in the impool block, so like implementation. This is actually very similar to this one here. But we are not implementing a certain interface for Pitcoin. We are just implementing the methods for Pitcoin. So it's just impool Pitcoin, and then you have your methods, right? So the first one will be marked with the inc constructor macro. And like I said before, the inc contract macro makes sure that you have at least one public method marked with the inc constructor macro. Now, in inc, because we use the macro and not just some special name like init or whatever, you can actually call this method whatever makes sense, like semantically. Because of that, we can have as many constructors as we wish and call them whatever we like. So it actually makes sense in certain use cases to not call them new, but maybe like enroll or whatever. And actually does a quite a simple thing, of course, leveraging our default method that we've learned on the previous slide. So we just say that, okay, let's start with the empty mapping for the balances. This will just give you an empty mapping because no one has interacted with the contract yet. We need to know the color, because if someone is calling the constructor, it's the owner basically of the contract. So the color is, well, there's a special self : env method that gives you all sorts of information about the environment in which the contract is executing in, including the color of a particular method. Now, if I create this contract, obviously I am the owner of the initial supply, right? I haven't transferred it to anyone yet. So we insert into the balances under the colors account, we insert the total supply, which makes sense, because for now, no transfers were made, no tokens changed hands, so the owner has all of the supply. And then we just instantiate the struct, actually using a shortcut, because usually we would write total supply, the field that's named total supply, colon, and would get the total supply of tokens, which we pass here as the argument of the constructor. And same for the balances. But if the value you want to assign to a certain field and that field's name are the same, you can just write the name, and the compiler will figure it out. It's a useful shorthand way to write this. Right. Just to for educational purposes, I wanted to show you the constructor how it used to be in inc 3.3. By the way, the inc that we're talking about now is inc 4. I'm not going to say 4.0 because it basically doesn't age well, but it's inc 4 with all the new goodies. But the old way was actually super educational, and a lot was happening here. So I'm going to just very briefly walk you through it. So in the olden days, we needed to call this special initialize contract method that was actually taking another function as the argument. And there you go. You have this is how you write anonymous functions in Rust, basically. Kind of similar to Ruby, actually, but with types. So you have the argument list in like double pipes, and then you have the argument names and the types, and then you just write out the body of the function in the curly braces. If you're interested what those ampersands here mean, those are references. And well, basically in Rust we say that the reference is borrowing a value. We're going to get to that, but It's kind of similar to C++ references if you're familiar with that. But basically what it does is that, like, lets someone else access the variable for a second and not necessarily copy it over and just cede ownership completely. If we append mutable to the reference, it means that someone we're giving this value to can actually mutate the value, which is actually cool, and it's very explicit. And if you remember what I said about making sure that you're quite careful about mutating your state and also about implicit stuff, this is cool because it's harder to mutate the state and it's very explicit. So I think that's good. Yeah. So that would be it more or less for the old constructor. Now notice how the self here is actually capitalized because it's and has double colons. Yeah, it's basically a static method, so like a method that you're calling on the whole class and not on a particular instance, which is important sometimes. Right, so I think right now we have enough information to move on to Rust memory management, which maybe is not, it's not crucial for you to be the expert on this when writing smart contracts, but definitely is a very interesting topic for a workshop. And of course, we're just going to scratch the surface, or not even that, but still, maybe it will get you interested in this area and lead you to your own research of this quite exciting area. So Rust is using the ownership model, which means that, I'm just going to read my slide. Each heap allocated piece of data has exactly one owner. You cannot access the data if you don't own or have been borrowed the data, right? So, and it kind of assumes that there are multiple people trying to access your data. Well, think of it as multiple scopes or multiple functions and so on, right? So the ways in which the ownership of a piece of heap allocated data can be transferred is twofold. So the first one is move. You might know this from C++ also if you know it. So move is when you're passing something by value or just assigning, you're basically giving away the ownership of the data. We're going to take a look at the examples later. So you're saying, okay, I'm done with this particular piece of data. I don't want to use it or modify it anymore or even access it. And then there's borrow, which is what is commonly known as passing by reference. And borrow is okay, you can take my piece of data. You can do some stuff depending on whether that's a mutable reference or unmutable. Well, you either can modify it or not, but surely you can take a look, and then you give it back to me, right? And the Rust compiler is able to track the ownership of each piece of data with basically compile time checks and zero overhead. So this is cool compared to a model where you would have to manually manage your memory access. And also cool compared to a scenario where you have a garbage collector and it can affect your program's performance in an unpredictable way, right? So here, this is actually the best of both worlds. So it's super efficient and there's no overhead, but yet you don't need to remember to free the memory or else you will have a memory leak. No, this is like the modern day stuff. Yeah, so to illustrate it on a very simple example, let's say that we have a struct with just one field, and then we instantiate it, and we say that there's a function where we pass it by value. So just no references, no anything. Okay, so we pass our struct by value, and what this function does is just increases the number that's inside the struct, right? So what do we expect, right? It looks simple, and in a lot of languages, this would work just fine, right? But here, we get a compilation error. So it says, okay, it borrowed and moved value. Okay, we're not going to perhaps get into the details, but well, you basically can instruct the compilers saying, okay, if someone wants to move this, you can actually copy the value over, but yeah, in this case, well, the problem is that once we move it to this function, we no longer have it. So we actually are moving it here, right? Here, this scope has foo, the scope inside of main. I'm not sure if you can see my cursor. And here we are completely giving away the ownership. So now when we try to access it in the line with print line, well, it's no longer ours. So the compiler tells us, okay, it's no longer yours to inspect. Like, no, you cannot do that, right? And the Rust compiler actually is quite helpful with all those messages, because it basically tells you what to do. Okay. Now we can fix this. Well, we'll see if we can fix this, but we can fix this by using passing by reference, so borrowing, right? Okay, so instead of just writing foo, we say this foo here will be borrowed. It will be passed by reference. Okay, so yeah, now it's good. We can see that no move occurs, and we should be able to use this foo here and access the field in the print line, right? Should work. But remember what we said about mutability. You need to explicitly say that I want the borrower to be able to mutate this reference, all the contents of this reference. And again, notice the Rust compiler telling us, okay, consider changing this to be a mutable reference. Okay, yeah, this makes sense, right? This is in line with what we've been talking about. So let's do just that, and we have a mutable reference. And actually, when you're passing by reference here, you need to also note that this is mutable reference here, right? And this compiles without problems, and actually even will display the value of 2 here at the end. Yeah, in general, I would avoid mutating data as long as your use case allows it, because it's easier in all aspects, but sometimes you just have to, and then you have to remember about the mutable. Yeah, by the way, WASM is heavily optimized towards working with references. So sometimes what people do is basically they will take the function and like delegate to the same function as the one being called, but with the arguments changed to references. It's actually it's fun stuff, but you'll see this quite a lot in the wild, let's say. Okay, so let's get back to well, after this longer side note, let's get back into our smart contract. And well, messages. So messages is, well, it's maybe not the best name. I guess it's kind of taken from the object-oriented programming world, maybe, where some people are calling methods messages. But this is basically like the public interface of your contract. So something that a user using the graphical user interface or some client or actually an application will be able to talk to your contract, right? So the first type of messages is like asking about the contract state. So the first message that we can ask the contract is obviously the total supply. And yeah, this is really simple. You just, this is a public function, well, method actually, that takes the self as the first argument. Interestingly, the methods need to have self passed as a reference. And passing self as the first argument is basically similar to what Python is doing. You just want to make it explicit, right? Some languages just give you the self implicitly, but we like to be explicit. So this is the philosophy in Rust. It actually makes a lot of sense, and we just say that it returns a balance. So this gives you just the total supply, so the total amount of tokens in your contract, right? So second type of a message is the balance of a certain account. And this illustrates actually a very, very, very important concept. So obviously, we will be getting the balance of a certain owner, which is an account ID. Now, remember our balances. It was a mapping. So when accessing the mapping, basically, we get two options. Either the key, so the owner here, the account ID, is in the mapping, in which case it's cool, we just return the result, or it's not. In which case, Well, some languages would throw an exception, some languages would throw an error or write some message. Here, they return like an option value saying, okay, there can either be something inside or there can not be. And we're using the unwrap or default method to say basically, okay, so whatever is in this result, if it's like a success result, so if the key was there, give me the value, plain value. And if it wasn't, give me the default, actually. Instead of some error message, give me the default. And the default for the balance is 0, as we remember. So notice how this like simple concept actually makes our balance of method very, very expressive, and actually makes it work with the whole like accounts model of this contract. So let's say someone has never interacted with the contract. So what balance they have? They have 0, right? If I want to transfer 100 Bitcoins to someone who has never used the contract, if this was returning an error, I would have to devise all this special logic for what happens when someone is, has never used the contract before and therefore is not in the mapping. But if I just say, okay, it's 0 if they're not in the mapping, I can just add it, and it just works so well. Yeah, so I really like this, well, algebraic error handling in general. Now here I wanted to make this infographic basically because I think the presentation looks way more professional when it contains an infographic. I'm not very good at it, by the way, and this concept is so simple that it really doesn't require one. But well, there you go. How do we make a transfer using our balances mapping and the whole model that we've devised, right? So let's say that Alice, notice that this is regular Alice, not Malice, like in the hack case. Her balance is 1,000 Bitcoins, and she wants to transfer to Bob 100 of her Bitcoins, right? Okay, so what the contract does is, well, obviously it needs to check whether Alice has sufficient balance. Well, obviously she has. So what are we doing now is, well, we are decreasing Alice's balance by the transferred amount, and of course increasing Bob's balance by the transferred amount. And of course, well, the balance is reflected at the end of the operation. And also note that by virtue of our unwrap or default implementation of balance off, if I always use balance off to send this to Bob, I can always say, well, balance off Bob's account. If he has never interacted with the contract before at this stage, it will just be 0. So I can also safely put whatever Bob's balance was plus 100 into the mapping, and it will work. So this is why I quite like it. So yeah, the sending and transfer is quite easy, but well, there's some code, mostly like not very interesting boilerplate, but nevertheless we're gonna inspect it. So the first thing is here. Here, this is the actual message, and remember what I talked about delegating to the same version of the method but with references. So this is exactly what is happening here. We are also kind of, well, we don't want the user to be able to have to provide their own account, because this kind of figures from who's calling the contract. So yeah, we will do just that. We will figure out the caller's address, and we will just pass it to the actual transfer method as a from. And yeah, so it does basically the thing we've just explained, but first it needs to check the balance of whoever is sending the transfer. Of course, if the balance is less than the value transferred, then we return some error, and we are actually gonna talk about what this error here means. But if all was good, we proceed, and to the balances, we of course first decrease the balance of the from sender. Obviously, we need to decrease the balance we had here, using references just because this is the implementation of the insert method. No need to worry about that for now. If you forget about it, the Rust compiler will just remind you in a very gentle way, so don't worry about it. Of course, the to balance is the balance of the recipient. So yeah, we use the same balance of method. Now notice again that if the to account was not in the mapping, it's okay, because this will just return 0, right? And we will, nevertheless, we will insert in under the to key, we will insert the previous balance plus the transferred value. So that, all good. Now we're also emitting an event and returning okay, but about that later. How do we handle errors? As you can see here, if something bad happens, we are returning an error of some sort. First of all, we start with defining our own custom error struct. We can, in theory, represent the errors as strings, or actually any other type you would like, even like numerical codes. But like the clean way would be to define a struct, actually an enum. So think of it as a variant type. So this enum can be constructed with one of the several constructors, depending on what is the actual error. Like in our case, from the transfer, if the amount you want to send is more than you have, you will get the insufficient balance error, right? Now, Rust has this way of kind of algebraically handling errors. So no exceptions, no weird execution flow breaks. We basically define another enum that I'm calling it my result, just to not introduce any conflict with the actual result name that's already in the Rust standard library, well, actually in the language, but the idea is exactly the same. So the my result can have two variants, either an okay, if everything was okay, and an error if something was wrong. Now it's parameterized by two types. So obviously the result is like, well, generic or polymorphic with regards to the stuff that we can put inside it, right? Because there can be like my result that returns an integer as the good value and maybe a string as the error, or it can return like some object when it's okay, and our custom error that we've defined on the previous slide when something's not okay. Now we can also do some type aliases, which is quite interesting, but also it's important to note that this is not type checked. So this is just a different name for the same type. It's not like the compiler will not be able to distinguish between my error written like that and my result written like that. But this is just a convenience tool for you. So yeah, so this is how we are going to represent our errors, right? We are going to return my result colon okay when everything was okay, and my result colon error if it was not okay. Actually, we're going to use without the my. We're just going to use result, and yeah, you can actually notice that this is way more expressive than just returning, like a Boolean value, true or false, whether the transfer succeeded, because this, first of all, this carries the information what actually went wrong. Second of all, the algebraic part that I mentioned is it's not some special language construct and doesn't interrupt the execution flow. You can just treat it as another value and act on errors as like part of your normal program's logic, right? Which is quite expressive and quite cool. Now, another thing we talked about we've seen like a teaser of in the specification and in the transfer implementation were the events. So events are basically how your contract will communicate certain events to the outside world, right? So just maybe wallets, maybe some indexers, maybe some explorers. Now it's just a struct with some fields of your choice, obviously what information you want to make available, marked with the inc event macro. We should be used to macroing important elements of the contract code by now. And for fields that you want to be like indexed, so if you want to search using this field, you would probably want to use the topic annotation, topic macro. Here we want to probably index the to and from addresses, but not the balance, because the balances of the transfer will be all over the place. So just like in a database, you wouldn't necessarily do an index on this one, but it will vary from use case to use case. Now, the interesting thing here is, why are the from and to fields wrapped in this optional struct, right? It's my intuition would be that the transfer should always have a sender and a recipient, but this can be left as an exercise. The way to emit an event is just by, again, using the end method and emit event, and you just need to instantiate the struct. And by the way, the asterisk here is basically the inverse of the ampersand. So it takes a reference and gets a concrete value out of it. Now, this way of emitting events will probably break if you use multiple contracts and cross-contract calls. In order to avoid that, there's some workarounds. You will find this in our documentation that was linked before. Now, you may remember from the explanation of the DAO hack that we talked about how you can actually transfer some actual chain's native currency into the contract. And I was saying that Solidity has this receive method. So Ink has a different way even of handling like payments in the native currency. So you are able to basically transfer some value alongside with the call, and which is quite cool. You can just, whenever you, of course, you will need to have the message here just to make sure that it's callable by your users. But also you need to mark it as payable so that the contract will know that it can accept the native currency as part of the call. It can be useful for fees or stuff like that. Now it's also important that you can you can access the transferred balance using this, again, the method from self.env. And perhaps an important notion here is that the contract on LF0, but on the substrate chains is an account. It has an account just like anyone else. So therefore it has balance, right? So it can accept the currency and so on. Right, now another important and maybe quite delicate aspect, because it's quite easy to get it wrong, and if stuff goes wrong, it usually goes wrong in this area, I would say. Cross-contract calls. So basically a contract calling another contract. Like, for example, a DEX will have to transfer PSP22 tokens, so it will need to call some methods from the token contracts, right? Now, there are two ways of making a call to another contract. One is more straightforward and concise. The other one is more low level and, well, a bit harder, but it does allow, if you remember from the previous slide, to send some native currency alongside the call. So pretty much I would say this is the only case where you would want to use the low level way. I guess in general, the easy way should be, and the like type checked and concise way should be preferred, unless you have a very good reason to use the more powerful version, but the harder version. But well, ultimately it's up to you, of course. Now the first version, the easy way, the Ink contract macro will basically generate a ref for your contract. So this will be like a facade, if you will, allowing other contracts to access certain methods from your contract, right? So importantly, it will be generated for you, but in general, it won't be exported, so it won't be visible from the outside. So you need to export it like this, right? I recall how use allowed you to bring stuff into scope. Pub use also like re-exports them to the outside. Okay, the color contract will basically just try to map the reference into here we also kind of try to initialize the reference from some account ID. This is important because a reference itself, well, says what is the type of the contract we're calling here. So basically, what's the class, but it doesn't tell the compiler what's the actual instance of the contract that we want to call. So in order to tell it what's the instance, we basically need to somehow initialize it with an account ID of a specific contract. Now, the important thing here is that when you're importing the reference here, the Rust compiler can actually check if what you're calling makes sense, right? If the type signature match, if the method exists. Yeah, and the as here is basically a cast, as you might know from other languages. In theory, it shouldn't be required, but the inferencer is basically it has a lot of work to do as is, and sometimes needs a little help. Yeah, so now the way of just building a raw call, which allows you to transfer some value to the contract. I'm not even gonna dive into the details. We also have a guide on that that's much more detailed because there's a lot of stuff to take care of. But the general idea is that you use a call builder, and you of course need to say what contract address you're gonna be calling. Then what's gonna be the input to the call. The idea of selectors is probably out of the scope of this presentation, but in general, you want to have like a number associated with each method so that you can transparently tell the execution input what method of this contract to use. And of course, you can export the selectors with the pub use so that you can just use aliases and not magic numbers. And then you push arguments. I mentioned the transfer value. And you need to say what's the return type. Note that this will be wrapped in one more layer of result because the call itself also can fail. And yeah, and then you just basically fire the call. So it's quite cumbersome, but if you want to transfer the value, that's what you're gonna do. Oh, I actually mentioned the selector already, but this is a way of assigning numbers to the methods that someone might want to call, and basically you can then make it as a constant and export it so that the colors of your method, like remote colors, won't have to guess them or put them as number constants in their code, which is usually a bad practice. They can just import what you will export here and just use it. And of course, you mark a method with a selector or a message in a similar way to marking it as payable, but you can put the value here as well. Now, let's say we have already created our contract. Now, we need to be quite careful with deploying the contract and in general executing it on chain, because basically there's a lot at stake, right? So of course, the first step is to write some unit tests to test the fine-grained functionality of your contract, but mostly the trivial stuff, but some invariants that you want to hold, or maybe here we want to change it. If we actually make the transfer, do the account balances decrease and increase as we expect, and so on and so forth. So yeah, they are just like Rust regular unit tests. You can just use some inf tests goodies for dealing with default accounts and simulating events and whatnot. Now the important part is that this is running on chain. On your local machine and not on chain as in contrast to the deployed smart contract, right? So this is cool because this allows you to iterate way more quickly. You also have end-to-end tests now with Ink. You will find that in the guides, but yeah, I think this is outside the scope of this presentation. So of course, the unit tests and the end-to-end tests off-chain are not enough, and if you try to deploy your contract, you first will deploy it on the testnet, and only after testing there for sufficient amount of time with real users, with doing like load testing and performance testing and trying to look for pitfalls and corner cases, and of course getting an audit, only then you'll probably go to mainnet and try to have actual users involved in that. So yeah, this is just good practice. Now you will notice that we are working quite a lot with the result types, and you may think that this is kind of repeatable and actually a lot of boilerplate. Now what we want to do here is basically somehow collapse that into something way more readable, like chain the operators, because we can see that both methods return the same type. The errors differ slightly, but that's okay. We still would like to chain them in some pipeline, and doing it like that seems like to defy the whole purpose of actually this whole algebraic result handling, right? So, well, if we just unwrap it and panic every time we see something bad, no, this is not the way to do it. So Rust has this very handy question mark operator that, okay, provided this one thing holds, so you are able to convert from one error to another. So like you can convert from my error 1 to my error 3, and similar from my error 1 into my error 2, and yeah, if you can like find a common type of errors and convert each error to the overall result of the function, you don't need to like unpack every value. You can just say, okay, this is the value that might fail, but let's treat it as a computation that does not fail. And if at any point in the chain of question marks this computation fails, we will basically return an error result from the whole computation. But inside this function, you can just treat them as functions that don't fail, like completely pure functions. But provided that you can do a conversion. Some common error types already have this conversion implemented in the library. Some do not. In which case you'll have to write an implementation quite similar to the default implementation we did, in the sense that the syntax is essentially the same. You just need to say, that this is the from interface for a specific parameterized by a specific error, and of course for another specific error. Now, yeah, I generally am very scared of doing live demos, so I've done some screenshots, but maybe we'll get some time to do the live demo as well. So yeah, basically, basically what you do is you go to the contracts UI, and assuming you have ran the cargo contract plus nightly build release command, you will have in your project, in the target/ink folder, you will have the contract bundle. And yeah, here under the add new contract, you will choose the account to deploy from. It will choose the contract's name and the bundle. It will get validated if this is like an even, correct file. Well, correct in a sense that it's not corrupted. Then you have this whole UI that will let you, say what parameter. Well, basically, you're calling the constructor here, right? So you're saying what initial parameters you're supplying to the contract. You get some gas estimations, which is actually quite a handy feature. You can use some more advanced features, but we're gonna skip on that completely because in general you're good with the defaults. And yeah, notice that this does like a small dry run of your contract, so it's also, you know, it can tell you whether this instantiation will be successful or not. It might not be, for example, if you don't have enough funds to pay for the fees. And also, by the way, note that on the LF0 testnet, you can just get T0 from the faucet, so you should always be able to experiment freely. And oh, actually, notice that this balance here, it's not the balance in T0. It's just it's showing us T0 here just because we used balance in the constructor, and it kind of assumes this is the chain's local currency, but this is actually our, well, Bitcoin in this example. This is just what we are initializing the initial supply with. We can pick any number we like. It's completely unrelated to the chain's native currency. Yeah, so you will basically get a model like this. You might want to copy the code hash. Well, sometimes you might need it, but okay. So now we have the deployed contract, and we can choose the message to send to the contract. Actually, notice that for like getters, so the methods that do not actually change any state, this doesn't need to be an interaction with the chain. It can just give you what's under there. I mean, like, you won't be making a transaction here or anything. Now you can also view the metadata, which is part of the contract bundle you uploaded. And yeah, important thing is that the metadata contains the stuff that you've put in as the doc strings. And so you probably want to be quite, you know, you want to make your comments or doc strings quite good, because there is a possibility that someone might need to read them and interact with your contract based on what they read here. So it's better to make them quite readable and informative. Yeah, we can, you know, if we have more than one account, we can transfer between those accounts. Of course, well, you don't need to own the second account. You can transfer it to whomever you like. But for the purpose of the test, I just basically made 2 accounts. And yeah, similarly to actually instantiating the contract here, I'm choosing the method, choosing the 2 arguments. The dry run is here, saying how much I'm going to be charged for the gas fees, and then I'm calling the contract, and I'm seeing some logs and events, which is yeah, which is basically how we interact with the contract. And well, we can actually very quickly go to the terminal, and I have a contract here that's basically the same Bitcoin that you've seen before. We can actually inspect its librs. Yeah, it's more or less the same, but with some additional comments and maybe some more functionality. Now I'm gonna just build it. Oh, well, there's no changes, so it was pretty quick and actually didn't do anything. But I can check the target inc folder, and you'll see that I have the contract file here. So okay, I know I'm good. I'm just gonna go to the smart contracts UI. Well, I already have it deployed, but this actually doesn't matter too much because I can deploy the same contract over and over again. I will just choose different names and I'll be all good, right? Make sure that you're on LF0 testnet. You can, of course, use the LF0 mainnet if your contract is audited and everything. But yeah, for the purpose of the demo, we will use the LF0 testnet. So I'm going to click Add New Contract and upload new contract code. Well, my account is here. By the way, yeah, you'll probably need the Polkadot extension or some other like signer like this, but I'm using this one. Contract name, we're gonna call it Bitcoin 2, and the contract bundle. Oh, I already have this conveniently in my, well, PSP this is not, oh, sorry, ink examples, and here is Bitcoin. Okay, so target, ink, Bitcoin contract. Okay, so yeah, we have some metadata parsed. The chain knows what is what. The ink version is 4.0.1. We will have authors just from parsing my cargo tunnel file. And then, yeah, then we can deploy the contract. Total supply will be whatever I want. And we can just upload and instantiate it. Of course, you will need to sign the transaction. And there we go. We have a contract. Like we said, we can inspect the metadata. It looks slightly different to what was on the presentation, because the other one was using night mode. And in the interact, we can check the total supply, check the balance of my own account. As we've mentioned previously, my own account has the whole supply. And we can, of course, transfer something. Let's use my second recipient and transfer them 1,000. Oh, actually, I could even transfer it to my other contracts, just because they are accounts, as we said previously. It's basically no transfer will actually be made. It will just be an updated, well, no A0 or T0 transfer will be made. It will just be an updated entry in the balance mapping, as you remember. But we can send it here and sign again. And yeah, the contract has, by the way, emitted an event, which is quite cool, which is what we expected. And now if we check balance of test recipient, yeah, it's denominated in different units, but that's basically the value we've transferred. So we're good. Let's get back to the presentation. And since this is mostly all I wanted to tell you about, it's time for some closing remarks with useful ink projects that I especially like. And this is one of my absolute favorites, the Inkathon by our friend Dennis Soma and Scilabs. So yeah, this is like a boilerplate for ink smart contracts with full stack. So basically, you get the contracts, you get the backend, you get the front end. It really can kickstart the development, and yeah, if you want to start quick, I definitely recommend it. Another thing that's I think it's a must if you're writing ink smart contracts. Sooner or later, you will either use it yourself or just encounter this in the wild. So OpenBrush is basically a smart contract framework, but you can think of it as a set of like batteries included primitives for creating tokens. So if you want a PSP22 token, you just create a struct and import the PSP22 trait, implement it for your contract, and you don't actually have to do much. If you want to extend it with some functionality, they also offer like a lot of extensions. You can just import them, implement them for your contract, and boom, then it's mintable or burnable or has access control. So this is an incredibly useful resource and very widely used. You can also give a try to Sol2Ink, which tries to migrate Solidity contracts to ink. Yeah, it should actually work quite nicely for smaller contracts, but you should give it a try. Definitely a very interesting tool. So yeah, that would be all. And if you made it to the end, here's one very virtual Bitcoin. Like I said, it doesn't exist. Well, actually it does, but it has absolutely no value. So yeah, here's a Bitcoin for you. And you may take a look at the special assignment. This is like a set of challenges if you want to really learn how to interact with the contracts and then really dive deep and maybe become like a proficient smart contract developer. This should be quite interesting. And Yeah, that's all for today. Thank you for listening. I hope I didn't bore you to death. And let's hope I will see you on the Aleph Zero Discord and Twitter and Telegram. And let's hope that you'll build some cool use cases for us to take a look at. So thank you very much and see you around.